AP Calculus BC, Unit 8, Day 3. This is the lesson. So we're going to continue on with series, building off of what we've done in the first couple lessons. You should be doing your assignments every day in this section. Otherwise, you're going to get lost real quick. You got to be paying attention. You got to be in class. You got to be taking notes. You got to be trying it yourself, because we're going to be building off of it every day. And this is so different than anything we've done. So, quick review: geometric and power series. So this is a geometric series that, sort of the first day we talked about. Power series is a geometric series, but you replace the r with x. Okay, so you get a polynomial. Okay. Other power series are built off this mothership, this kind of most basic power series, by changing r, integrating, differentiating, adding different series together to form a new series. So we can get a lot of different series from this. Okay, we call this one when r equals a number, which it was for us the first day. We call that a number series instead of a power series. So power series are series that have number series. A power series is a series that has variables in it. Okay, variables to powers usually. Okay, other power series for well-known functions. If you plug in r equals negative x squared, and by the way, this is the sum right here. That's the sum. So the sum, we're using this formula to kind of help us create these other series. So in this case right here, this is the a value, r equals negative x squared. If you plug it in, the first term is 1, then you multiply by negative x squared every time. You get this polynomial with even powers and alternating signs. If you were to integrate this, integrate both sides, 0 to x dx, what would the antiderivative of 1 over 1 plus x squared? Well, that would be inverse tangent. And the antiderivative of 1 is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus ... You can integrate this term right here. The sign in front of it should stay the same, right? But power rule, you bump it up 1 and you divide by the new exponent. So this is kind of this function, this polynomial function right here actually represents inverse tangent if you take all infinite terms. Okay? And this is how our calculators do it. They actually use something like this to calculate inverse tangent. Now, if you plug x equals 1 in, inverse tangent of 1, well, what angle do you, if you solve this just on paper, if I say, well, what would you take tangent of what angle to get 1? Well, that's when sine over cosine give you the same number. That's pi over 4, quadrant 1 or quadrant 3. This is principal values. And so you could also plug 1 into this. For all the x values and keep this going. And all of these actually add up to what pi over 4 is. So if you want an approximation for pi, it's kind of an interesting way to find an approximation for pi. I think we've looked at other versions of approximation for pi. You can multiply both sides by 4, and it would be 4 minus 4 thirds plus 4 fifths minus 4 sevenths, and on. Now, if you take all the terms, it's actually exactly pi. If you just take a certain amount of them, then you get an approximation for pi. The more terms you take, the closer it is. So this converges for x equals 1, even though the original power series did not. We'll look at convergence closer later, like next unit. For now, just enjoy that work. So most of the intervals of convergence we talked about, like on this, the interval of convergence, negative x squared, that's the original series before we integrated it. The r value, the absolute value of r, has to be less than 1. And absolute value, get rid of the negative. It's going to be squared, so it's going to be forced to be positive. And so this is the interval of convergence for the original series. Okay. And so you would think it follows that the interval of convergence for this series would also be the same thing, but there's going to be some exceptions. Okay, so 1 is on the border. We shouldn't be able to use it, but it actually works. And I can show this. We'll try this on a calculator. Now, so we could actually say, yeah, let's look at the partial sums, by the way. This is kind of an interesting idea that we're going to be doing a lot of. So partial sums, we start talking about those on the first day as a way to kind of sort of see what the behavior of a series was as you add it up. Partial sums are the sums as you go. So the first partial sum, I'm going to kind of draw this a little differently just to kind of illustrate what's happening and just to kind of be able to try and draw a picture that goes with it. So it starts at 4. The first partial sum is 4, right? And then when you subtract 4/3, you get 2 2/3, which is, which would be kind of like right over here. 2 2/3 would be the next partial sum. So we started here and then we ended up over here. The next partial sum, you add 4/5 to this. So 2 2/3, that's 8/3 plus 4/5. So what's 8/3 plus 4/5? Least common denominator would be 15. So it'd be 40 plus 12 is 52 over 15. We get 52 over 15. So that would be 3 7/15. 3 7/15, which is almost halfway, right? 3 7/15. 3 7/15 would be the next partial sum. So we come back to here. Now, I'm not going to do the work for all these, but the next partial sum is 2 94 1/05. So that's kind of like right here, 2 94 1/05. I mean, you could do the work. And then the next partial sum is 3 37 3/15. So it's almost about 3 1/3. So like right around here, 3 37 3/15. Okay. But what you can do is you can tell just from this picture that we're getting closer and closer. We're going back and forth, past it, going past it, back and forth until we're approaching, a certain value. It's going to keep going. And that value is pi, 3.14. We're approaching it. So, I mean, if we were just looking here, we could do 4 minus 4/3 plus 4/5 minus 4/7 plus 4/9 minus 4/11 plus 4/13. You can tell this is getting closer and closer to 3.1, right? It keeps overshooting and undershooting it. Minus 4/15 plus 4/17 minus 4/19. I mean, it's getting closer and closer to 3.14, right? Plus 4/21 minus 4/23 plus 4/25 minus 4/27 plus 4/29. I mean, it's gonna get there, right? So it's interesting. That's how our calculators actually work. They don't take all the terms. They take a certain amount of terms that will give a reasonably accurate answer. The more terms you take, the more memory it takes, the more computation it takes. But, that was, I don't even know how many terms. That was like just like 15 terms. God, it was getting us pretty close. Okay. Let's look at some others. What about when r equals negative x? This is the sum. So that's the function it represents. The first term is 1 multiplied by negative x times negative x times negative x. This is the pattern you get. This is the open form. And let's integrate this one. And I think we did something like this or the same thing as this the other day. So let's integrate both sides. You're allowed to do that in math. You can, as long as you do one thing on one side, balance it out. You can get natural log of 1 plus x. Now, I know we usually put absolute values, but we're not going to this time. I think the main reason is we don't need these is because x is between -1 and 1 for interval of convergence, so it's going to always be positive. The antiderivative of this is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5 dot, dot, dot. Now the general term, the -1 to the n, don't integrate that. That's just a number. Whatever it is, if it's negative, it's going to stay negative, right? The thing with an x in it is the thing you have to integrate. Bump it up by 1, divide by the new exponent. So that's the general term. Okay. If you're to plug x equals 1 to this would be the value of natural log of 2. 1 minus, and you plug 1 in for all the x's. And if you took all of them, it would actually equal natural log of 2. Now, this one actually does converge for x equals 1, even though I talked about it on the last problem. That's usually the border where it doesn't. This is a special kind of series, by the way, that we're getting right here. It's called an alternating harmonic series. So harmonic series is where the denominator just increases by 1 every time. Alternating means it's switching between plus and minus, plus and minus. Okay, so we're going to see a lot of alternating series, but that's a famous series. Okay, can we find a power series for the function e to the x? Now, so I guess I'm sort of toying with the idea that maybe we could kind of figure it out. That I doubt that, but I think we can use some things that we understand about e to the x that you could follow it. We know that the derivative of this function is itself. So can we find a power series where the derivative is equal to the original series? Okay, so I'm going to help you out here. I don't think anyone would have guessed this, but here's a series that I think might work. Okay, you shouldn't feel bad if you're like, there's no way I could have figured that out. So check this series out. Let's write this series down. Now those exclamation marks are factorials. You guys should know how to do factorials. Factorials, it's that number times every integer below it down to 1. Okay, we could write this in closed form with the sigma notation. If we start at 0, the first term, it's going to be x to the n over, and you could even think on this first one, that'd be 1 factorial. This would be 0 factorial. Actually, this is like x to the 0. That's like x to the first. So if you were to just write n equals 0 and n equals 1, you'd see a very clear pattern that it's x to the n over n factorial. Now, you guys should know how factorial works. Like 3 factorial is 3 times 2 times 1, which would be 6. It gets big really quick. It's the fastest growing function, even faster than exponentials. 2 factorial will be 2 times 1 times 2. 1 factorial is 1. Now, here's a crazy one. I'm not going to get into it right now, but 0 factorial is 1. Okay? And there's a way to prove it, but I'm not going to get into that. This factorial stuff really shows up, I think, like algebra 2. So you should already kind of have a background in this. But just refreshing your memory, because in any factorial, you can actually write, like if you're going to do 5 factorial, that's actually 5 times 4 factorial, because 4 factorial would include all the rest that 5 factorial would have. And so we're going to use that to help us simplify things. Anyways, this is an interesting function because check it out. Let's take the derivative of it. I mean, I'm kind of setting you guys up for things to work out nice, but the derivative of 1 is 0. Goes away. The derivative of x is 1, plus the derivative of that's going to be 2x to the first over 2 factorial, plus the derivative of x cubed is 3x squared over 3 factorial, plus 4x cubed over 4 factorial, right? plus 5x to the fourth over 5 plus ... And even the general term, we could say, well, there's an n in front, and it's going to be x to the n minus 1 over n factorial plus ... equals, you can even take the derivative here. So if you multiply n in front and then decrease the exponent, right, and then you have the n factorial on the bottom. Now check this out. Let's simplify this. 2 factorial is just 2, so those reduce. 3 factorial is 3 times 2 factorial, right? So we could write it, just leave a 2 factorial there. 4 factorial is 4 times 3 factorial, so we can cancel 4s out, leave a 3 factorial. So each step we go, that new number on the top reduces with the first number on the bottom, and if we were to rewrite it nicely, we get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus ... plus even here, n factorial is n times n minus 1 factorial. So the n's cancel. Now, if we write x to the n minus 1 here over n minus 1 factorial, we're going to have to start our closed function at n equals 1. We could, rewrite it so it starts at n equals 0, and then it would look exactly like the first one. You say, oh, well, it's just going to be x to the n over n factorial then. Right? Okay. So it's the same as the original function. And we said that e to the x is its own derivative. In fact, it's the only function we've ever seen that is its own derivative. And guess what? E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial. This is a very, very common function that you need to be very familiar with. Open form, closed form, starting at any n value. Okay? And so that is, we're going to just memorize it. Okay? We're going to memorize it. And there's a couple other really common functions that are very close to this that will make it easier. This actually converges. So we've been talking about convergence, interval of convergence. On a lot of these, it's a very narrow window, -1 to 1 only would be the only x values that it works. But this one actually converges for all real x values. It's kind of crazy. Okay? Not just -1 to 1. Okay? We'll talk about these issues later. Okay? I'm not going to get into this weird stuff. Like I said on day 1, let's roll with it. I will show you later. Now, so if you wanted a value of e, you could actually calculate the value of e from this function. If you plug 1 in for all the x's, if you were to add all these up to infinity, you would get e. Now, that's impossible to do, to actually carry out physically, but that's the idea. It converges to e. Now, if you just wanted to take a bunch of the first terms, that would give you a pretty good estimate for it, and that's how our calculators do it. Because the only operations involved here, which is our calculators, computers, can only do addition, subtraction, multiplication, division to accomplish every single thing that your computer or calculator does. Not just math, everything. But for math, to get a value of e, this is how they get it. So, kind of interesting. Okay. Now, here's the thing. That one we kind of stumbled upon. Like, well, how are we going to do this because we can do this for every single function out there, we can create a series for. And just trying to guess it or follow someone else doing it, that's not going to work very well. So there's actually a process. There is a way to find the series for any kind of polynomial. Okay, so we're going to talk about a more specific type of power series called a Taylor series or a Taylor polynomial. Can we design a series for any function? Yes, if we have enough information. We need to know the center of where we want the function to converge. Okay, and we need the values of the derivatives at that center. And if we have that, this power series, this is it. So we talked about series, then we talked about a specific type of series called geometric series, then we talked about a specific geometric series called a power series, and now we're talking about a specific power series called a Taylor series. We're going down, 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 right? So we went from series to geometric series to power series, and now we're going to Taylor series. And there's even another one after that. We're gonna talk about right now. Start with the center. We're gonna make it a little easier. We're gonna start with the center at 0. So that's the center of the. When we say center, we're talking about the center of the interval of convergence. So it's kind of like, well, where are you planning to use this series for? What kind of values? That will direct how you design it. But if the center is at 0, that's a special type of Taylor series called a Mclaren series. So that's an even more specific series, a Mclaren series. And we deal with a lot of Mclaren series. So we're getting more and more and more specific. Okay, so this is how this works. Let's find the fourth order Taylor polynomial. So a polynomial isn't a series. It's not an infinite series. It's a finite series. We only take a certain amount of terms, which is more realistic. That's what our calculator does, takes only a certain amount of terms. And the more terms you take, the better it gets. The less terms, the less better of an estimate is. But okay, for some unknown function. Now, fourth order means that the highest power on an x is going to be x to the fourth power. So it's like the same idea as like the degree of a polynomial. Okay, if it says fourth order, fourth degree. Okay. Now, they've given us all the values of the function and its derivatives up to the fourth derivative. We need that at the center. Okay. And so we're trying to find this polynomial, capital P for Taylor polynomial, and a sub 0, a sub 1, a sub 2, a sub 3, a sub 4 are the coefficients, and that's what we're trying to find. We're trying to find a polynomial that's going to fit this function, generic function, okay? So here's the process that we got to find these. We got to solve for these, and all the values of the derivatives are going to help us do that. Essentially, it creates a system of equations, okay? So like the derivative of this, remember these are just numbers, so it's going to be, that one drops out, a sub 1 plus 2 a sub 2x plus 3 a sub 3x squared plus 4 a sub 4x to the third. And then we take the second derivative, that one drops out, and we get 2 a sub 2 plus 6 a sub 3x plus 12 a sub 4x squared. Take the next derivative, that drops out. We get 6a sub 3 plus 24 a sub 4x the first. Take the fourth derivative, that drops out, and we get 24 a sub 4. Okay? So now we have a system of equations. We have 5 equations with 5 unknowns. Okay? That we should be able to solve it with that. Okay? The equations come from, we're going to plug 0 into the x's and set it equal to 2. So starting at the beginning, the first one, p sub 0, okay, is going to just equal a sub 0. All the terms with x's are going to be zeros. They drop out. And we know it's supposed to equal 2, right? Okay, cool. So we just found a sub 0. We found one of the 5 things. So we're going to use that approach. P prime 0 is going to equal a1. And we know that it equals 3. So we have that, okay? Then we're going to do P double prime 0. And all the terms drop out except for 2a sub 2. And it's supposed to equal negative 4. And so then if we solve for it, we get a sub 2 equals negative 2. Cool. 3 down, 2 to go. Then we do P triple prime 0. And we get 6a sub 3. And we know that the third derivative is supposed to equal 5. So then we get a sub 3 equals 5 over 6. And one more to go. Fourth derivative, 1, 2, 3, 4, is just going to be 24a sub 4. And it's supposed to equal 2. So a sub 4 equals 2 over 24, 1/12. Okay? Now we have all the values, so we can plug them back into the original and say, okay, the first one is 2 minus 2x plus 5, 6x squared. Oh, wait, I missed one. 3x plus 3x minus 2 minus 2x squared plus 5, 6 x cubed plus 1/12 x to the fourth. So this is your Taylor polynomial to represent this function. Now, we don't even know what the function is, but we have the derivative value. So now here's the deal. We don't want to go through all that work every time, okay? And there's some special patterns that come out of this, okay, that actually are kind of related to what we were talking about on the front with factorials. Check this out. 2 is the same thing as 2 over 0 factorial, okay? 3 is the same thing as 3 over 1 factorial. Negative 2 is the same thing as negative 4 divided by 2 factorial. 5, 6 is the same thing as 5 divided by 3 factorial. 1/12 is the same thing as 24 2 divided by 4 factorial, okay? There's a very clear pattern here, okay? These numbers that showed up in front, they're just factorials, right? Isn't 2 2 times 1? Isn't 6 3 times 2 times 1? Isn't 24 4 times 3 times 2 times 1? The next derivative would have a 5 in front, And so every time you take another derivative, it just builds on that factorial. And then when we want to solve for these coefficients, we have to divide by that extra number in front, right? So here's the better way to think of this. Right from the beginning, if we understand this, if we accept this, right from the beginning, we could say, okay, the first term is going to be the original function, 0th derivative, essentially, over 0 factorial. The next one is going to be the first derivative over 1 factorial. The next one's going to be the second derivative over 2 factorial. The next one's going to be the third derivative over 3 factorial. The next one's going to be the fourth derivative over 4 factorial. So the derivative values go right over the factorial values. And that's how it's going to work all the time. That's the quick way. We don't want to go through all this work every time and solve a system of equations. So here's the conclusion. To create a Taylor polynomial, or even a Taylor series, a Taylor polynomial is finite terms. A Taylor series is infinite terms. So we're going to be dealing with both of them, okay? The more reasonable application of it is finite, because even computers, as fast as they are never going to finish an infinite calculation. But here's the derivative. Here's the deal. Now, A is the center, okay? Notice that we said it was centered at 0, so we had to find the 0th, the value of all of these derivatives with plugging 0 in. So that's what's right here. The first term is always going to be like the original function, kind of like the 0th derivative over 0 factorial. And then I forgot to put the x's on here. This should have an x. This should have an x squared. This should have an x cubed. This should have an x to the fourth. Now, something that we didn't really get into here is that the x actually will always have the center subtracted from it before it gets raised to that power. Since the center was 0 here, they just ended up being x, okay? So it's always going to be, we're going to be using this so much, so you need to be able to like crank this out from memory, no problem. And it's some pretty clear patterns here. It's the derivative of the function at the center times x minus the center to that same power over 0 factorial. So we have the derivative, 0th derivative, 0th power, 0 factorial. First derivative, first power, first factorial. Second derivative, second power, 2 factorial. Third derivative, third power, 3 factorial. All these numbers all line up. I mean, that should make it easy, okay? And then you always plug the center in to the derivative, and this is always going to be x minus center. If the center is 0, then this just becomes x. So that's a special case called the Mclaren series, when the center is 0, which is very common. This is the pattern it takes, but it's the same pattern, just with zeros plugged in for the a values. Okay, so this is a huge deal, okay? We're going to use that so much. So now let's go ahead and do it. Let's construct the power series for sine x, centered at 0, okay? Construct the power series. Okay, so we're going to do this. Now, the one thing we need, the thing that takes a little bit of work, is we need the derivatives for as far as we're going to go. Now, we're going to say series, so that means we want infinite terms. So we're really going to try and find a pattern. So we'll find a bunch of derivatives and then try and use the pattern from it. Okay, so the original function that we're trying to build a series for is sine x, right? And so the first derivative, this is like the 0th derivative. The first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. The fourth derivative is positive sine x, right? And then it starts to repeat itself. I'm going to go and write a few more down just to make it super clear. So then the fifth derivative is cosine x. At some point, we write little superscripts in parentheses to represent derivatives, so we don't have to write all the primes. Negative sine x. Seventh derivative, negative cosine x. Eighth derivative. I'm going a little overboard this time. But anyways, okay. And then we can keep going. Okay. So we need all those derivatives. This is how we're going to do it anytime. This is faster than the way I showed you, but we're going to have to maybe find all these derivatives. Then we got to find the value at the center. So we need to find the value of the function at 0. We need to get those numbers. Sine of 0 is 0. Cosine of 0 is 1. And negative sine of 0 is 0. Negative cosine of 0 is negative 1. Fourth derivative at 0 is going to be 0. Fifth derivative of 0 is going to be 1. Sixth derivative at 0 is going to be 0. Seventh derivative at 0 is going to be negative 1. Eighth derivative at 0 is going to be 0. Okay? We're getting there. It's a little tedious. I mean, it's not hard. This is easy work, but it is a little tedious. So then we're ready to go. We're ready to use this formula. Okay? So sine x equals the first, that's the coefficient. Each of these end up being part of the coefficient in front, and then it's x minus 0 to the 0th power over 0 factorial. And then 1 x minus 0 to the first power over 1 factorial. And then 0 times x minus 0 to the second power over 2 factorial. And then negative 1. Now I'm writing this as if it was centered at something else. Now, because you know it's centered at 0, you could just like say, oh, let's stop writing the x minus zeros. I'll do that maybe on the next step. So you're like, oh, yeah, let's just write x to the fourth. And then the fifth was 1. But it's the fifth derivative of 0, x to the fifth over 5 factorial. Everything's 5, right? Let's go and write a few more terms here. 0, x to the 6th over 6 factorial. Negative 1, x to the 7th over 7 factorial. 0, x to the 8th over 8 factorial. And then it keeps going if it's a series. Okay? Now, check it out. I think we could write this. 1, all the 0 terms drop out, right? Half the terms drop out. We don't need to write those. What's left, if we simplify it, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. Could you predict, could you come up with a formula for this? Like we have, I feel like there's a pattern here, right? So if you look at it, you can help yourself out. We could start, at n equals 0. If you write the n values next to the terms, I feel like it makes it easier for me to look for the pattern. So if you look, this is x to the first, third, fifth, seventh. There's this number that shows up all over the place. So it's going to be the same. Look at this. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 is 4 plus 1. The pattern is x to the 2n plus 1. And the number on the bottom is the same thing, 2n plus 1 factorial. But there is a positive negative flipping in front. The way you accomplish that is you have a negative 1 to the n power. If we start at n equals 0, that'll give you a positive. Plus dot, 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 dot. So this is the open form of the power series for sine. Now, we could write the closed form. We could say n equals 0. This is called the general term, by the way, which you're often going to be asked to write. And the general term is what we put inside of our closed form anyways. If you guys can read that. So there it is. We're going to memorize this one because that's a lot of work, even though it wasn't that terribly hard. It was tedious, and this comes up a lot. So could you guys could do it for cosine. Now, I'm going to tell you, once you're done, you're going to start to notice some patterns here. Now, doesn't this kind of look like the e to the x series a little bit that we did on the front here? That we're going to memorize. It has all these factorials in it, except the sine is missing all the even terms. It's missing all the even terms, x to the 0, x squared, x to the 4th, x to the 6th. Oh, okay, so sine has all the odd terms. Now, by the way, sine is considered an odd function. And so that's the way I remember it. Now, when you do cosine, if you work it out, you get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. The pattern is going to be negative 1 to the n again. It's going to be x to the, if you write n equals 0 here, n equals 1, n equals 2, you'll say, oh, it's going to be x to the 2n over 2n. And you need to put parentheses around this. Because order of operations, factorials, are like exponents, and they take precedence over parentheses, or over multiplication. So you got to put parentheses around these for that to be accurate. That's cosine. And guess what? Check it out. It's the exponential. It's e to the x without all the odd functions, but also the alternating part is that this is an even function. So I remember I can memorize all three of these together. E to the x, sine x, cosine x, because sine x and cosine x are just half the terms of e to the x. with a plus or minus pattern thrown in. And sine is odd, so it's the odd terms. And cosine's an even function, so it's the even term. So I totally have all three of these memorized now. Okay. All right. Today's assignment out of your Calc BC book, page 480, you're going to do a couple more exploration problems. On page 483, you're going to do 68, 70, 71 all, and then 72 just parts A and B only. And then on page 492, you're going to do problems 2, 3, 5, 8, 15. You have to do these, okay? Now, by the way, here's another clever way of getting the cosine series. If you have the sine series, isn't cosine the derivative of sine? Take the derivative of all these. Guess what you get? You get this. It's amazing. You can actually take derivatives of a series to get another series too. I mean, that would be the faster way of doing it, right? Okay, do the homework. This is critical stuff. This first week of series is the biggest deal. Okay, you have to be on it every day.